The process of evaluating quadratic expressions was pretty straightforward, regardless of which form the quadratic was in. However, as we progress to solving quadratic equations and graphing quadratic functions, we're going to want the flexibility of changing the form of the quadratic that we're looking at so that we can solve or graph more easily. Generally, this will involve converting into the factored form or the vertex form, which is easiest to do when starting from the standard form. But what do you do if the expression you want to convert isn't already in standard form? Well, you start by converting it into standard form, and then you convert it into the form you really want. In this video, we'll focus on the first part of that process as we convert quadratic expressions into standard form. Recall from an earlier video that the main properties of the standard form were the absence of parentheses and like terms being combined. And while combining like terms is an important skill, the heart of converting into the standard form will be eliminating parentheses. And our method for eliminating parentheses will be distribution. Take this expression. Inside the parentheses, we have a quadratic that's already in the standard form. But that expression is being multiplied by a constant. So how can we eliminate the parentheses and see the true standard form? Well, we simply distribute the 3 to each term inside the parentheses, and after multiplying each of those terms by 3, we get this result. And if that's all it takes to eliminate parentheses and convert to the standard form, we should be set. Well, unfortunately, it's not quite that easy, because there's another way to multiply two polynomials and get a quadratic result. When we have the product of two linear factors, which is the factored form, the result is also a quadratic. So how do we convert that into the standard form? Well, the answer is once again distribution, but we're going to have to be more clever with how we distribute. The key here is to think of one set of parentheses as a single unit that can then be distributed across the other set of parentheses. This process isn't too different from the distribution that we've done before. We just have to distribute an expression instead of a number. The unfortunate part, though, is that our result is still not in the standard form. In fact, we still have two sets of parentheses. But notice that our sets of parentheses are now separated with addition instead of multiplication, which will come in handy since we can now simplify these two sub-expressions separately. But how should we simplify each of these sub-expressions? Well, with distribution, of course. Once we go through a second round of distribution, we can see that we've successfully eliminated all the parentheses, which means that we've met our first criterion for converting into the standard form. To finish this problem off, notice that we still need to meet the second criterion for converting into the standard form, which is that like terms are combined. And in our current expression, we have a single quadratic term and a single constant term, but notice that there are two linear terms. So let's combine those linear terms, which allows us to write our final expression and achieve the standard form. As we continue to convert quadratic expressions into the standard form, we'll need to use this prolonged distribution process for many of the problems that we encounter. Because of this, let's give this process a name. And since we had to do 2 rounds of distribution to get our final result, let's call this process double distribution. There is an issue with this double distribution process though, which is that it's a bit tedious. Thankfully, there's a way that we can simplify the process and still get the same result. So let's check that out before moving on to our next section. When we do the double distribution process, we're essentially taking each term from the first set of parentheses times each term from the second set of parentheses. So instead of writing things out this way, what we can do instead is this. Notice that each term from the first set of parentheses was distributed over the second set of parentheses, and the final result is the same as what we achieved earlier. Thus, moving forward, we'll use this simplified double distribution with the knowledge that it actually represents a longer process. With that, let's practice converting some more quadratic expressions into the standard form. We'll start with another expression that's in the factored form, and as we demonstrated in the last section, we'll do our simplified double distribution here. The first product that we get is x times x, which is x squared. Then we do x times 8 to get our next term of 8x. But instead of adding 8x, we need to subtract 8x since we were subtracting the 8 in the second set of parentheses. Next, we do the same process with the 5. 5 times x is 5x, and 5 times 8 is 40. But we need to once again subtract 40 rather than adding 40. Then we can combine our like terms to get our final answer. Now, most of what we just did should be familiar from the example in the last section. But if you have any uncertainties about when to use a minus sign versus a plus sign, you're probably not alone. Dealing with combinations of negative numbers and subtraction is one of the more challenging aspects of distribution. And as we transition to double distribution, these challenges can get even worse. What we need then is a strategy for handling these challenges in a deliberate and methodical manner. And the best way of doing that is to turn all of our subtraction into addition. Unfortunately, that doesn't mean that we can just replace our minus signs with plus signs, because that would change the value of the expression. What we can do, though, is add negative numbers instead of subtracting, which gives us 4x plus negative 9 times x plus negative 1. Now when we distribute, we don't have to worry about whether we should add or subtract any particular term. Since our operations within each factor are addition, we can use addition between every pair of terms in our result. This gets us 4x squared plus 4x times negative 1, which is negative 4x. Then we do negative 9 times x and add that result in. Finally, we do negative 9 times negative 1, which is positive 9, and we add that onto our result as well. At this point, we can reinterpret some of these signs. Instead of adding negative quantities, we can now think of those as subtraction, which allows us to rewrite our expression this way. And finally, let's finish off the problem by combining like terms, which once again gives us the standard form. Note that while we could have gotten this result in a more straightforward manner, changing our subtraction into addition of negative quantities helped us manage our signs much more consistently. We'll complete our next example in a similar manner. So instead of keeping the first factor as x minus 12, we'll rewrite it as x plus negative 12. Then, when we do our double distribution, we get two terms with negative coefficients thanks to that negative 12. Then, we combine our linear terms to get our converted expression. And for one more example of this process, here's our final problem for this screen. One aspect of the factored form that we haven't explored yet is when we have a constant factor separate from our two linear factors. So let's try a problem that's set up that way. A common temptation here is to distribute the 3 to all of the other terms, which would look like this. This is incorrect, however, and we can see why by taking a closer look at the overall structure of this expression. If we temporarily cover the 3 and each set of parentheses with their own individual boxes, we can see that this expression is just the product of 3 distinct pieces. We could even represent this situation with 3 variables, like a, b, and c. In the expression a times b times c, we're allowed to multiply those pieces in whatever order we want. thanks to the commutative and associative properties of multiplication. So, we could think of this as A times B times C, or as A times C times B, or as B times C times A. What we can't do, however, is multiply both B and C times A, since that would incorporate A into the final product 2 times instead of just once. So let's look back at our original expression and decide which of these pieces we want to multiply first. Suppose we choose to start by multiplying these two together. That's a simple distribution process that gets us 3x plus 12. Then, we would still need to multiply that by x plus 5, which would look like this and result in this answer. However, we could also have chosen to start by multiplying the two linear factors first. In this case, we would temporarily ignore the 3 and do our double distribution between these pieces. Then, once we get a result for our first product, we would distribute the 3 to finish things off. And of course, we could have also chosen to start by multiplying the 3 times the second linear factor and gotten the same result. Regardless of which method we choose, notice that none of these match our initial attempt at distribution, since the 3 can only be distributed over one of these linear factors, not both. Let's follow that up with a similar looking example, but we'll throw in some subtraction and negatives this time. As we demonstrated previously, we can manage our signs by rewriting the subtraction as addition of a negative quantity. However, similar to how the double distribution process can get a bit cumbersome when we write everything out, it can also start to feel a bit cumbersome to rewrite all of our subtraction this way. So instead, let's go back to the original expression and mentally think of this as a negative 4, even though it's technically written as subtraction by 4. Next, we need to decide which two factors we want to multiply first here. While any order will work, it's probably easiest to multiply the two linear factors first. That way, we can get the double distribution out of the way before we complicate matters with an extra factor. So let's do that double distribution, and when we get to this step, remember that we're going to think of it as negative 4 times x, which is negative 4x. And then we get negative 4 times 2, which is negative 8. Additionally, note that when we wrote down these results, we wrote them with subtraction instead of adding a negative quantity, which also allows us to reduce the number of steps that we're writing out. Then, after we combine the like terms for the expression inside the parentheses, we can finish things off by distributing the negative 6, which gets us this result. Now that we've looked at several examples of converting the factored form into the standard form, let's try a couple examples that are in the vertex form, starting with this expression. While this may initially look quite different from the factored form, it turns out to be surprisingly similar. Since squaring can be thought of as repeated multiplication, we can simply write the expression inside the parentheses twice. Of course, we still need to include the minus 11 afterwards, but this first part looks pretty familiar. Then, we just do our double distribution to get this expression, bring down the minus 11, and combine the like terms to get our final result. This next example has an additional constant factor in front of the perfect square, but that won't end up changing much about the conversion process either. We do need to think a bit more carefully about what's being squared, but once we identify that the exponent is attached to the parentheses, we know that we should only repeat the expression that's inside the parentheses. This gives us the following expression, where we can once again focus on the linear factors and perform double distribution. After that, we distribute the 5 and combine the resulting constant term with the remaining term of 22 to get the standard form. On our final screen, we'll do a few more examples, including a couple examples that start with quadratic expressions that aren't in any particular form. Despite their unique forms, note that the process of converting these expressions to the standard form isn't all that unique. We simply follow the rules of distribution that we've been working with this whole time and finish things off by combining like terms. That concludes this video on converting quadratic expressions into the standard form. Hope you learned something new, and thanks for watching.